This lecture will be on reaction energy diagrams or profiles. And we're going to study two different reactions, but that appear the same in a superficial way. Basically, it's just a simple substitution reaction. We have molecule AB reacting with anion C. And we can see that when the reactants react, the products are anion A, and then molecule B, C. So C has substituted A in this reaction. Some terms we will use in looking at the energy diagrams are E sub A, which is the activation energy, and we can define that when we actually look at the diagram. This symbol, which is kind of like a T with a double crossbar, stands for the transition state. And this will be during a reaction, the least stable or the highest energy species that's formed in a reaction. And we'll see that and where it appears on the energy diagram. And then delta H, which you're familiar with, which will be the enthalpy of the reactions. We're talking about the energies in making bonds and breaking bonds. If this reaction was to occur in one step, we can draw an energy profile that is fairly simple. These reactions potentially can be exothermic or endothermic, but we'll just be showing exothermic reactions. On the y-axis is just energy, and so the higher energy means less stability throughout the reaction. And then the x-axis, moving in this direction, is called the reaction coordinate or reaction progress. And basically we're talking about time. If you're thinking of starting with reactants and as they go to the products, if that process takes time. In our one-step reaction, if we start with reactants here, we would have A bonded to B and anion C. Up at the top of this hill, the highest energy point, that would be the transition state. And we'll think about what that would look like after we draw in the products. The products then over here would be anion C, or anion A, and molecule B, C. We can see that the products are lower in energy than the reactants, and so the distance in energy between these two would be our delta H, or our enthalpy. So if there were units on this axis, we would know the enthalpy of reaction. The difference in energy from the reactants to the transition state, or the highest energy point, that's going to be your activation energy. And so it's basically the amount of energy it takes in order to get to the highest, most unstable point, and then when you progress downward, you're releasing energy from that point. And so you need to have enough energy, or the energy of activation, in order to go from reactants to products, as this is drawn up. In this reaction, if it's a one-step reaction and we think about what the transition state might look like, well, on this side, A is bonded to B, and C is not bonded to anything. On this side, A is not bonded to anything, and B is bonded to C. So in the middle, A must still be somewhat bonded to B, and C must be somewhat bonded to B as well. So it's kind of a position where a bond is breaking and another bond is being made simultaneously. Hence, it's a one-step reaction. So in the transition state, we can envision this species that would be quite unstable because it kind of has partial bonds instead of concrete sigma bonds. And we can represent that structure with these dashed lines, so kind of a partial bond. And so basically, C had a negative charge, and as it donates its electrons to forming a bond, it's going to lose part of that negative charge. And so C will only have a partial negative, whereas A, where it had this bond here, if those in the products, it has a full negative charge, it must be developing a partial negative charge as well. And the total charge on this species, since we reacted a neutral with a negative, must overall be -1. And so this would be essentially what the transition state looks like. If we wanted to draw a mechanism for how this occurs, which is something we'll introduce now and we'll get into in subsequent chapters, but we can draw how these species interact and see how that might translate to this transition state. If we think about molecule AB, and this is not part of the reaction diagram, simply the mechanism. If we think about molecule AB and it's reacting with anion C, just like we've done before with some resonance structures and we moved electrons, we can move electrons between two different chemical species when they react. And so if the lone pair on C begins forming a bond to B, while at the same time the bond between A and B is breaking and those electrons are going to A, we can represent that with these arrows. And so at the same time C's electrons are forming a bond, the electrons shared between A and B are just going to A. And so this mechanism actually ties into the transition state, and we can see perhaps how these two are related. And this then gives us our overall products. The same reaction can actually occur in 2 steps instead of 1 step. Our axes will be the same. We'll make this an exothermic reaction as well, where the overall products are more stable, lower in energy than the starting materials. And so we see in the energy profile we have 2 humps instead of 1 for each step. And so we're going to see 2 transition states and 2 activation energies and 2 reaction enthalpies, as well as an overall reaction enthalpy. And so if these are our starting materials again here, AB, and then anion C, and our products filled in a similar fashion, we can think about what the transition states and the intermediates might be. Well, this will be transition state 1, and this will be transition state 2, progressing from reactants to products in a logical way. And then this here, which represents kind of a stable point, or the most stable point between the 2 transition states, will be our intermediate. And so we know what the structures of the reactants and products are. If this is a 2-step reaction, the structure of the intermediate could be where you've broken the bond between A and B, such that now A received the electrons and has a negative charge, and now B lost electrons and has a positive charge, and C did not react in this product, in this process. And so going from reactants to this intermediate is requires energy. And so we can think about that in terms of bond making and bond breaking. If all we did was break a bond, then that always requires energy, and so we've gone upwards, or increased in energy and decreased in stability. Once we go from the intermediate to the products, where now we've made a bond from C to B, we have an exothermic process. And this too will go through a transition state. The activation energy for the first process would be the energy difference between the reactants and the transition state. The activation energy for the second step of this reaction would be between the intermediate and the second transition state. And so we can see the second activation energy is much smaller than the first activation energy in this specific diagram. We think about delta H. Our initial delta H is positive, or required energy to get to the intermediate. The second enthalpy would be from this same position down to the final products. It would be a negative value since we've released energy. And then this total reaction would be similar to the first one. And so the difference between the ultimate reactants and the ultimate products we could describe as delta H reaction or delta H total for the entire process. And thinking about what the transition states look like for this reaction, we can think about the reactants and products of each individual step. And so in this case, if all we've done is broken the bond between A and B, in the transition state here, C is not involved at all, because C doesn't change going from reactants to the intermediate. However, A and B are involved, or the molecule AB is the only thing involved, and we can see this bond breaking apart. We're beginning to develop a partial negative charge on A and a partial positive charge on B. For the second transition state, here we can see that A doesn't change, going from this reactant set to the ultimate products, and so A won't be involved. Technically, we don't need to even draw them in, although they might be present. And so here we're forming a bond from B to C, B going from a total positive charge to neutral. In the transition state would have a partial positive charge. C then would have a partial negative charge as it goes from negative to neutral. And we can draw in transition states like such. If we want to draw a mechanism for this reaction, since it's two steps, it will require two steps in a mechanism. If we describe the reaction as such, what we can see if we use arrows is that only one thing happens at a time. And so in the first reaction, where the bond from A to B is broken and those electrons go to A, that would be the first step in the sequence. And notice C is not involved. In the second step of the sequence, where C is involved, this would be where the electrons from C form a bond to B. And we end up with the final product. One thing to point out in this diagram before we move on, we can use these two activation energies to think about which one's going to be the faster step in this process. The slowest step in the process is going to be called the rate determining step. And so the rate determining step of a reaction is what determines the rate, but it's the most important one in thinking about how fast a reaction is going to go. And so if it requires the most energy to get to this point here, then this step will be the slowest and will determine the rate. And the second step will be relatively much faster than that first one, and so it won't impact the rate, because essentially as every molecule that can get to this point in the reaction is likely that it will overcome the next point very, very quickly relative to another molecule being able to overcome that first hill in the diagram. In thinking about rates, they're affected by a couple different factors. First of all, the activation energy of that specific reaction. Secondly, temperature. So the temperature is a direct measurement of how much energy is available. And so the higher the temperature, the faster molecules will be able to get over that hump, because on average there'll be more energy around. And so temperature plays a crucial role. The last one is concentration. And so we're talking about specifically the concentration of the reactants involved in that step. And so the more concentrated they are, the more likely they are to react with one another. And so as you increase the concentration, the rate increases as well, as long as you're increasing the concentration of a reactant that's involved in that step. An equation for a rate might look something like this. It's relatively simple. What you have is a rate constant for that specific reaction, and then it shows that the concentration of the reactants are intimately involved with that. So this rate constant will take into account the activation energy for that specific reaction and the temperature at which that reaction was carried out. And then that only leaves concentration that involves in the rate. Rates are measured essentially in inverse seconds. And what that means is how many times per second something occurred. And so if a reaction has a large rate, or a large value for the rate, that means many events are happening in a certain amount of time. So fast reactions have large rate constants. If it has a small rate constant, then that means only relatively few events are happening in a certain amount of time. And so that would be a slower rate. So small rates mean slower reactions. If we think about our one-step reaction, we can write an equation for the rate that looks like this. In this one-step reaction, both molecule AB and C, anion C, were involved in that step because it required C forming a bond to B as this bond was breaking. So both reactants were involved. Since both reactants were involved, both of their concentrations are important for the rate. Because both are involved, the reaction is referred to as second order. That means you basically have two different things determining that rate, or the concentrations of two different reactants determines that rate. We can say that the concentration of AB and of C affects the rate for this particular reaction. If you were to increase the concentration of, say, AB, let's say double it, and we apply that to this concentration here, essentially if we double this, we'll be doubling the rate because we're just multiplying by 2 in this set of numbers. And so if you double the concentration of AB for this particular reaction, you double the rate. And so this literally means if you double the concentration of your reactants in a particular reaction, then it will go twice as fast. And logically, since anion C is also involved, if you double the concentration of anion C, you will also double the rate. And likewise, if you tripled this concentration, you would triple the rate. Same thing for anion C. If you cut that concentration in half, the rate would be cut in half. And so it's a logical relationship. If you were to double both A and B and anion C, then since you would be doubling both, you would be quadrupling the rate because you can be multiplying by 2 and then by 2 again. For the two-step mechanism, where we started with the same reactants, but in the first step, C was not involved, and in the second step, A was not involved, well then that's going to impact the rate. And so the rate equation is a very simple expression, and it only involves AB. If we go back and look at the energy diagram, the one that I just erased, we're only concerned with the concentration of AB because that was the first step of the reaction. And it's not important because it was the first step, but it's important because that step had the highest activation energy. And so that was the rate determining step of the reaction. And so that's the one that's going to impact the rate. And so since C is not involved with that step of the reaction, it's not involved, its concentration effectively does not matter in determining the rate. The only concentration that matters is the concentration of molecule AB, because that was involved in that step. Well, basically all it does is bust apart. This reaction then is first order in terms of the rate, because only the concentration of only one molecular species is important. Hence, if you were to triple the concentration of AB, then you triple the rate of the reaction. You have 3 times as much of this in a particular volume, then you'll have 3 times the reaction rate. If you triple or double or do anything to the concentration of anion C in this reaction, the rate is unaffected. Again, because anion C is not involved in this step that is rate determining. So this should serve as an introduction to reaction rates and some mechanisms that we're going to study in great deal in chapters 7 and 8. This is covered in chapter 6 of the textbook, and you can look over some of their diagrams that might offer some more detailed or specifics about these two situations.